Hi everyone, I'm Cheryl. In this problem, we're asked to find the interval of convergence for 4 different series. We're going to begin with the series that's the sum from n equals 0 to infinity of x over 3 to the nth power. I notice that this is a geometric series, and I know that geometric series converge when the common ratio, which in this case is x over 3, when the absolute value of that common ratio is less than 1. So that tells me that the absolute value of x all over 3 must be less than 1, and the absolute value of x has to be less than 3, which tells me that x must be somewhere between -3 and +3 in order for this series to converge. So my interval of convergence is -3 to +3. Okay, let's take a look at another series. Now, my second series is related to the first one. It's the derivative of that first series. So let's go ahead and find the derivative. Well, first of all, I'm going to rewrite that expression just a little bit and write this as the sum from n equals 0 to infinity of x to the n all over 3 to the n. Now we're ready to take the derivative. Now notice we're taking the derivative with respect to x. So 1 over 3 to the n acts as a constant multiple. So when I take my derivative, I end up with this series from n equals 1 to infinity of 1 over 3 to the n. And then when I differentiate x to the n, I have n x to the n minus 1. Notice that my index changed from a 0 to a 1, because remember, when n equals 0 up here, this term will be a constant, and the derivative of a constant is 0. So that's not included in my series. Okay, now, one thing that's interesting to note is that when I take the derivative of a series and I know what the interval of convergence is, it's going to have the same, what we call radius of convergence. So I know that this new series will converge from -3 to +3, just like the old series did. However, there might be something different that's happening at the endpoints. So I need to find out what happens at -3 and at +3. So let's check that out individually. So we'll check what happens at x equals -3. At -3, my series is going to be the series from 1 to infinity of 1 over 3 to the n times -3 to the n minus 1 power. Now I can rewrite this as my series from n equals 1 to infinity, and I can notice that this -3 to the n minus 1 can be written with a -1 to the n minus 1 power, and my 3 to the n minus 1 will cancel with the 3 to the n that's in the denominator, leaving just a 3 in the denominator, and I still have that n in the numerator. So it simplifies to this series. All right, well, let's take a look at this particular series. It is an alternating series. However, I notice that if I take the limit as n approaches infinity of my terms, n continues to get larger and larger. So n divided by 3 will also get larger. The -1 will make it a positive or a negative. Well, what happens with that? Well, I'm going to end up, when n equals 1, for instance, with a 1/3. And when n equals 2, -2/3. Then a positive 3 over 3 and a negative 4 over 3. And what's happening is that the limit is definitely not equal to 0. So this particular series diverges by the nth term divergence test. All right, let's go ahead and check what happens when x equals +3. So we'll check what happens when x equals a +3. When x equals a +3, my series is the series from 1 to infinity of 1 over 3 to the n times n times 3 to the n minus 1 power, which is my series from 1 to infinity of n all over 3. Again, because the 3 to the n minus 1 cancels with the 3 to the n. This particular series also diverges because of the nth term divergence test, because if I take the limit as n approaches infinity of each of those terms, I don't get 0. So it diverges by the nth term divergence test. So my interval of convergence, again for this problem, is -3 to +3. Now let's clear the board and we'll take a look at the next two examples. So the next series that we're going to be looking for the interval of convergence is that of the second derivative. And we already found out that the first derivative is the series summing from 1 to infinity of n over 3 to the n times x to the n minus 1. So if I take the derivative of that, I notice that because I'm differentiating with respect to x, the n divided by 3 to the n acts as a constant multiple. So I will have my sum going from n equals 2 to infinity of n all over 3 to the n. And I need to differentiate the x to the n minus 1 power. So I'll bring down the n minus 1, copy over the x, and subtract 1 from the exponent. So that gives you x to the n minus 2 power. And again, we notice that index, I'm starting at 2 now, because when n equals 1, this will be a constant, and the derivative is 0. And so that term is not included in my second derivative. All right, so I know that the interval of convergence is going to be similar to the intervals that I had before. In fact, the radius is still going to be 3. So I know it's convergent between -3 and +3. But once again, I need to check the endpoints. So let's go ahead and see what happens to this series when x equals -3. So we're going to check what happens at x equals -3. My series then becomes the series from n equals 2 to infinity of n times n minus 1 all over 3 to the n times a -3 to the n minus 2 power, which is going to be my series from n equals 2 to infinity of, I've got a -1 to the n minus 2 power floating around, and then I have a 3 to the n minus 2 divided by 3 to the n. That's going to leave me with a 3 squared, or a 9 in the denominator, and then I still have my n and my n minus 1. Okay, now if you take a look at this particular series, and I take a look at the limit as n approaches infinity of my terms, again, that numerator is going to continue to grow, and I'll divide by 9. So this entire piece, without the toggling, is going to get larger and larger. The -1 will just make one term positive, one term negative, positive, negative, positive, and so on. So by the nth term divergence test, I can see that this will diverge. So this is going to diverge by the nth term divergence test. Okay, now I have to see what happens at x equals 3. So let's check x equals 3. All right, so what does my series look like now? I'll have the series from n equals 2 to infinity of n over 3 to the n. And then, of course, I'm multiplying by n minus 1. And I'll have 3 to the n minus 2 power. And this will simplify to the series from n equals 2 to infinity of n times n minus 1 all over 9. Again, I have 3 to the n minus 2, which will cancel with 3 to the n, leaving me with a 3 squared, or 9. And again, by the nth term divergence test, this particular, the sequence here does not equal 0. And so the limit as n approaches 0 of this sequence does not equal 0. So my whole series diverges by the nth term divergence test. So I'm looking for, again, for that interval of convergence, and my interval of convergence is going to be from -3 to +3 because I don't want to count either one of those endpoints. All right, last piece. I want to look at the interval of convergence for the integral of f of x dx from 0 to infinity of x over 3 to the nth power dx. Okay, so what I'm going to do is I'm going to rewrite this, and I'll sum from 0 to infinity. I'll write that as x to the n all over 3 to the n dx. Okay. Now again, because I'm integrating with respect to x, that 1 over 3 to the n is going to act as a constant multiple. So I'm going to have a series n equals 0 to infinity of 1 all over 3 to the n, and then I'm just going to integrate x to the n, which is x to the n plus 1 all over n plus 1 plus a constant. Okay, so again, in this particular example, I just have the integral of what I already know is a geometric series, which is convergent between -3 and +3. This one will be convergent on that interval as well, except that we have to check those endpoints, just like we've done all along. So let's see what happens when x is -3. When x is -3, my sum is going to look like the sum from n equals 0 to infinity of 1 all over 3 to the n times -3 to the n plus 1 all over n plus 1. And then I still have that constant of integration here. Now when I'm checking for whether or not this series converges or not, that constant is not going to have an effect on it. If this series converges, then the whole thing will converge. So let's see what that is equivalent to. I have the sum from n equals 0 to infinity. I'm going to have a -1 to the n plus 1. And I'll have a 3 to the n plus 1 and a 3 to the n down here. So the 3 to the n will cancel, and I'll be left with a 3 in the numerator, and my denominator will be an n plus 1. Now this particular series is an alternating series. And if you use the alternating series test on it, you will find that this series converges. So it's going to converge by the alternating series test. All right, one last thing to try. We have to check what happens when x equals a +3. And at a +3, we're going to have the series n equals 0 to infinity of 1 over 3 to the n, a 3 to the n plus 1, all over n plus 1 plus my constant. Okay. And this reduces to a 3 all over n plus 1. Now this particular series, if you use the limit comparison test and compare it to the divergence series 1 over n, you will find that this particular series diverges. So diverges by the limit comparison test. So what does that tell me about the particular series? It converges at -3 and it diverges at 3. So this one is different. Its interval of convergence is the interval from -3 to 3, including -3. I hope that was helpful. Thanks.